Hi, I'm Today I'll be presenting OrbitalBrain, Harnessing Distributed Training in Space. This is a joint work between Channing, Kevin, Santiago, Ben Naz, Peter, and Renvier. As we've seen over the last few years, the resolution quality of satellite imagery has gotten extremely precise. This imagery has been used for numerous applications ranging from forest fire detection to flood detection to even normal just agricultural monitoring. And as time goes on, this resolution continues to increase. For instance, on planet's newest satellite class, they're aiming for a 1 meter resolution. And these satellites are starting to become equipped with high powerful GPUs like NVIDIA's GPUs. And as this resolution goes higher and higher, what you'll see is that there's an explosive amount of growth in the amount of data that these constellations are capturing. So for instance, here on the left, I have a plot on the number of satellites that Planet has. And what we've seen is that it's exploded to nearly a few hundred satellites that are continually capturing photos every day. And on the right here, we have a graph showing the amount of data that each one of these satellites captures. And we're nearly at the point where they're capturing 25,000 photos a day. And increasingly, as this graph continues, the amount of data in each one of those photos is also increasing. So as a result, we're seeing an exponential growth in the amount of data that this whole entire constellation captures. So if we just look at one singular satellite, let's explain what happens. So as the satellite is traveling across the Earth, it'll continually capture all of these photos. And then whenever it comes into contact with the ground station, it'll start to downlink a lot of these photos that it captures. At once points downloaded, these images will be transferred to the cloud where some model can be run, and then increasingly a user can access them. However, what we'll see is that this downlink from the satellite to the ground station is becoming extremely constrained to the point where this is not simply scalable to the amount of data that's becoming. In fact, as we zoom out to the whole entire constellation, you'll see that all of these X's here are satellites, and all of the green are obviously ground stations. And what you'll see is that no matter what happens, there's a constrained downlink between the satellite and the ground station. And what you'll see here is that this is really the core bottleneck. And so even if we apply compression, which in this case we use 3x compression, which is the state of the art at the time of this paper, what we saw is that only 30% of the captured data reaches the ground. And even if you were to deploy new ground stations or new compression algorithms, this is only a very linear scaling. So here in OrbitalBrain, we asked a very natural question of, can we do everything in space? So increasingly over the last few years, we've seen so many papers which can push inference to the space of how can we run models which detect, say, forest fires on the Earth. And here we asked, can we even train those models in space? And can we just run everything in space? And there's hopefully at first you might be saying, what? Why are we doing this? But hopefully here with the motivation, I can convince you that this might be a possible solution which can happen in the future. And so what we're seeing is that one, all of these new satellites are being equipped with increasingly more and more powerful compute. Two, these satellites are equipped with stronger and stronger inter-satellite links. Three, all of these satellites are run by one or two organizations which allow for permissive capabilities. And four, these satellite orbits are extremely predictable. So one, let's talk about why there's more compute in space. Increasingly on every single one of their satellites, Planet Labs and other similar satellite operators are adding GPUs to their deployment. The default case is, say, an NVIDIA Jetson GPU, which is just a small low-cost GPU, which is designed for, say, mobile devices. Increasingly, we're even seeing, though, H100s being deployed on these satellites. For instance, they just launched a test one with one of these. And this is motivated by a lot of reasons, specifically because the more compute that you can do on space, the less you have to transfer to the ground. Similarly, we're seeing that intersatellite links, which are basically lasers that allow one satellite to directly talk to another satellite just over the air, these are increasingly becoming deployed and they allow for substantially more amounts of communication. So here on the left, for instance, I plotted the ground to satellite connections for the whole entire constellation over the day. What you'll see, though, is that there's maybe on average around 15 to 20 satellite GS to SAT connections. And once you consider energy, it's under 10 on average. Now, on the other hand, if we look at the amount of satellite to satellite connections which are possible, you'll see on the order of 10,000 satellites, of 10,000 connections are possible. And even if we consider energy, you'll see that it only drops to around 5 to 6,000. So these allow for much more frequent communication patterns, unlike the ground to sat connections, which you have to make many hours to connect to. Similarly, what you'll see is that while intersatellite links have a much higher bandwidth, sorry, much higher variance in the bandwidth, the maximum intersatellite link communication is much more than a ground to sat because an intersatellite link has an uninterrupted laser communication as opposed to having to go from space all the way down to the Earth. Similarly, what you'll see is that satellite orbits are extremely predictable. Because they're following a fixed pattern around the Earth, which is governed by physics, they cannot move and deviate substantially from their orbit over the course of, say, 5 or 6 hours. In fact, previous studies have found that even though they're at so high in space, they can be predictable to a few kilometers. And as a result of this predictable in the orbit, you can also predict many other downstream things. For instance, energy is extremely predictable because it just has to deal with whether the satellite is in view of the sun or if it's covered by the Earth. Likewise, link data rates are also extremely predictable because it's mostly a function of where the satellite is relative to the ground station. And those can be predicted to 1 or 2 dBm. Finally, what you'll see is that there's a highly constrained budget in terms of energy. A satellite only generates around 7 watts of power from their solar panels. Now, downlinking all the way from space to ground takes around 50 watts. And similarly, if you were just to run your GPU, this is NVIDIA Jetson, with an intersatellite link, it only takes around 7.5 watts, which is much cheaper in terms of power. And finally, what you'll see is that storage is limited. So onboard storage limits force you to make decisions because there's only 360 GB roughly on board. So you can't keep storing all of your data across a whole entire day as you start doing as you look at the full constellation. So then we present OrbitalBrain. So OrbitalBrain is a new scheduling framework which allows for distributed training to happen in space. In OrbitalBrain, there's 3 possible decisions which a satellite does at each window, which is roughly every 5 minutes. One, a satellite can do local compute, which is that it can take all of these samples that the satellite itself has collected and train on those locally. 2, it can do model aggregation, which basically will take all of these different satellites as local models and combine them together. 3, we allow for data transfer, which basically allows raw data that a satellite takes to directly transfer with another satellite's raw data. So let's first talk about who actually runs what in OrbitalBrain. So at the first is the core, which is our cloud, like a data center on Earth, which runs a scheduling platform, which will then get which will then get uploaded. Our ground stations act as simply a relay, which they forward control messages whenever a satellite comes into pass. And then finally, satellites will execute their assigned decisions by the cloud. So just to reiterate this, if we look at the data flow on the left here, whenever in contact with the ground station, the satellite will send their local model updates, their energy and storage status, and any updated images that they'd like to send to the ground. The ground station will send a new compute schedule and a new data model transfer schedule up to the satellite. And then the satellites will execute and transfer data when scheduled by that platform. Similarly, if we look at the scheduling framework, which runs on the cloud, there's 4 steps. There's the performance profiler, which happens every single time a satellite comes into contact with a ground station. It'll basically send some profile updates, which will then be used in our future scheduling framework. There's a model aggregator formulator, which basically will formulate when satellites should share models with each other. There's a data transfer formulator, which will decide when satellites should send raw data with each other. And then there's an executor, which will combine all of these. So first, let's talk about the first step, the performance profiler. The idea is that whenever a satellite comes into contact with the cloud, the satellite will download all of these data. For satellites that are not currently in view, the cloud will keep an update based off of when it was previously in contact and basically update locally an estimation of all of these variables. So one, we have stillness, which is basically when was the last time the satellite had their model aggregated. 2 is the samples that they used. 3 is the predicted compute, basically how much energy do they likely have to perform training. And 4 is the last observed loss, basically what is the local training loss. Then once we have this performance profiler, we get into this model aggregation mechanism, or MA mechanism. The key idea here is that we want to use ISLs to keep these models fresh and up to date from each other. These non-ground station satellites will participate in aggregation through routing through these ISLs, and this allows communication across the whole entire constellation. So let's first get into when we should perform local compute, and that'll inform when we can perform model aggregation. So let's first ask, when is it most valuable to actually just train on the data? So it's most valuable whenever, one, they have a lot of data, and two, they have a lot of energy, and two, they have a lot of samples which are far away from the current model. However, if you have a very old model, it's not beneficial for you to spend your energy local training because you're just going to be fine-tuning a very crappy model, which is not up to date with the whole entire constellation. So then we get into this idea of when can we balance compute versus model aggregation. And the idea is that we only want to do model aggregation whenever it's actually beneficial over each satellite doing their local compute. And this is determined by the average staleness across the whole entire constellation and the amount of energy spent to do this aggregation. And so the idea is that we want to allow this constellation to first do local training, and then as time goes on, aggregate their models more. And what you'll see here is that because of this model aggregation, we're able to reduce this thing called staleness. So on the x-axis here, we have staleness, which is the number of windows of a satellite having the local model updated. And on the y-axis here is the CDF. And what you can see here is there's about a 4x improvement in staleness once model aggregation occurs. So then we get this idea of data transfer, which is that we want to fix non-IID, that is independent data at the source. So basically what you'll see is that since each satellite has a fixed orbit, every satellite will overfit to their own local data distribution. So for instance, here we have a 60 class classification task. I'll get into more details in the eval section. But what ends up happening is that over the first, let's say, 1.5 hours, they'll only collect 30 or 40 data labels. And as a result, if they were to train on that, that would end up overfitting to their local data. And this is not beneficial in terms of energy and compute. So to do this, whenever a satellite comes into contact with the ground, they calculate the JSD. That is, we calculate a number representing the IID distribution. Then the cloud will basically calculate, based off of that satellite, every satellite they can come into communication with, what's the actual beneficial for it to be transferred. And then finally, we basically will take all of these links and determine whether or not the transfer utility is actually better than just spending that energy on just training the model itself. And what we'll show is that we only do this whether it's actually beneficial over just simply training on your data. And what we'll see here is that by actually using data transferring, we're able to reduce the average IID across the whole entire constellation. So then we get into our experimental setup. We use TLE traces from Planet-inspired constellations. We use Lincoln data rate modeling that Planet has released. We use energy and storage also from Planet data. And then here on the slides, I'll report results from FMOW, which is a 60 class classification class, but we have more tasks in the paper. Let's first look at the final accuracy. What you'll see here is that bent pipe, which is the normal way of just downlinking data to the satellite, produces around 47% and 50% on Spire. However, OrbitalBrain is able to beat this by 52% and 59% respectively. Similarly, if we look at the time to achieve the same accuracy as BEM-pipe, we'll see around a 1.55x and a 1.52x. So basically we're around, what used to originally take 1.5 hours now takes around 1. And finally, we show an ablation study. What you can see here is that whenever we disable model aggregation, we'll lose around a 15% accuracy. And whenever we disable data transferring, we'll lose around 11% accuracy. And in both of these cases, we'll have a slowdown of 2.5 and 2.2 respectively. Thank you for listening.